Hello again. In these presentations we will be talking about sensitivity analysis. Remember that the simplex method was published by George Dantzig in 1947. In those years, there were no computers, not even calculators. All the computations were done manually. You may not know it, but the simplex method is based on inverse matrices. And the matrix dimension depends on the number of constraints in the problem. If we had a big company and one of its problems had 30 constraints, the number of computations to solve this problem would be enormous. Furthermore, if one of the values of the variables is modified in one of the equations, we should have to solve the problem again from scratch. To avoid doing so many computations from scratch, a brand of linear programming was created. This brand was called sensitivity analysis. The intention of these presentations is not to explain the mathematical fundamentals of sensitivity analysis, but to explain how it can be used in the business world. Let's go to the office to talk about this subject. Let's assume that a company produces wooden furniture. In particular, the company produces chairs, tables and armchairs. The relevant information is summarized in this table. Each table must spend 3 hours in the carpentry department, and 3 hours in the painting department. Its maximum weekly demand is 100 units. And the profit generated by each table is $72. Each chair must spend 2 hours in carpentry, 1 hour in upholstery, and 2 hours in painting. Its maximum weekly demand is 500 units. The profit generated by each chair is $27. Each armchair must spend 2 hours in carpentry, 3 hours in upholstery, and 1 hour in painting. There are no demand constraints. And each armchair generates a profit of $90. Weekly, there are 1,000 hours available in the carpentry department, 700 hours in upholstery and 800 hours in painting. On the other hand, since many customers who purchase tables also want to purchase chairs, an extra requisite is that the number of chairs produced must be at least twice as much as the number of tables produced. The formulation for the problem is the following. We have defined M as the number of tables, S as the number of chairs, and SI as the number of armchairs. Remember that when the formulation is captured in Lindo, you must consider that the last constraint must be entered as S minus 2 times M, greater than or equal to 0. And in this occasion, when you run Lindo, I ask you to request the sensitivity analysis. I have written some notes in the problem to remind us about the meaning of the constraints. The Lindo output report has 2 parts. The first part shows the results and the shadow prices. The second part shows the intervals in which the resources and the coefficients of the variables can vary. The row marked as number 1 shows the objective function value. Immediately after, the optimal value of the variables is displayed. In this case M is equal to 89.47. S is equal to 178.94. And SI is equal to 173.68. Recall that the simplex method finds continuous solutions, which means that the numbers in the solution are not necessarily integers. On the other hand, there is a second column denominated reduced cost. This column would have values different from 0 if the values of M, S or SI had been 0. In a future example, I will explain the meaning of this value. The third part of this section is numbered from 2 to 7. Each row is associated with one of the 6 constraints in the problem. The first constraint corresponds to the number 2. In this case we can see that in the column named slack or surplus the number 26.31 is shown. This number represents the non-utilized resource 1. That is, from the 1,000 hours available, we have utilized 973.69 hours. Now, imagine that you are given an additional hour of this resource for free. Actually, you would not utilize this additional hour. The only thing that would happen is that there would be 27.31 non-utilized hours, but the value of the objective function would not increase. The dual price, or shadow price, indicates how much the objective function increases for each additional unit of this resource. Therefore, in this case the shadow price is 0. This is the meaning of the shadow price, which is the value that appears in the third column. Now then, if we had 1 hour less available of this resource, then the value of the objective function would not change, but there would be 1 less non-utilized hour. But then, it is obvious that this shadow price does not always have the same value. Since we only had 200 units available of the first resource, the objective function would change. The question then is, in which interval the shadow price is 0? The answer is found in the second part of Lindo's report. Those answers assure then the shadow price of the first resource is 0 in the interval 1000 minus the allowable decrease and 1000 plus the allowable increase. That is, the shadow price of the first resource is 0 if the availability of the first resources varies between 973.68 and infinity. In the case of the second constraint, there are 700 hours available. Since the value in the slack or surplus column is 0, it means that we have used all the available hours. In this case, the value of the shadow price is 26.52. Which indicates that if we could have 1 more hour of this resource, the objective function would increase by $26.52. But if we had 1 hour less available, then value of the objective function would decrease by $26.52. Furthermore, the shadow price will keep its value as long as the resource of this constraint remains in the interval between 700 and the allowable increase or decrease. Therefore, if for some reason we had made a mistake and it turns out that the number of available hours in upholstery is 600, the value of the objective function would be 24,252.63. Even though nowadays the result can be obtained by changing the constraint and running the program again, imagine the effort that had to be made to solve the problem in 1950. The interpretation of the obtained results for the third constraint is very similar to the interpretation made for the second constraint. We only have to be careful reading the data. We now move on to review the fourth constraint. As we can see, the maximum demand of the tables is 100 units and we only produce 89.47 tables. This means that we have a slack of 10.53 units. And because of the observed shadow price, we know that if the demand increases, there would be no change in the objective function value. Besides, from the report we know that this shadow price does not change if the resource varies in the interval 89.47 to infinity. Therefore, if a company seeks to sell you a marketing campaign to increase the demand of the tables, you should decline the offer. The interpretation of the fifth constraint is very similar to the previous one. The sixth constraint says that the number of chairs should be at least twice as the number of tables. If you see the number of tables and the number of chairs in the solution report, you will observe that the constraint is satisfied in the limit. That is, we are producing exactly twice as many chairs than tables. This means that the slack or surplus is 0. If the constraint said that the number of chairs has to be 1 unit more than the number of tables, then the constraint would change to the following expression. The value of 1, that now appears on the right-hand side, must be interpreted as, the resource has increased in 1 unit. And because of the shadow price, we know that when the resource increases by 1 unit, the objective function value decreases 20.36 units. And if we were allowed to produce one chair less than twice the number of tables, the objective function value would increase 20.36 units. This is the correct interpretation of the report for the last constraint. Finally, let's take a look at the last part of the report. These lines are related to the coefficients of the variables in the objective function. The lines indicate the range in which the coefficients of each variable can vary, and the solution to produce 89.47 tables, 178.94 chairs, and 173.68 armchairs, would not change. For instance, in the case of the coefficient of the variable m, its coefficient is 72, and it could increase by 504 units or decrease by 66 units, and the solution would not change. That is, the coefficient can vary between 6 and 576. This means that if the profit is $10 per table, or $550 per table, the optimal quantity to produce would be the same. In the same way, we can find the intervals in which the coefficient of S, and the coefficient of SI, can vary. I hope this explanation has been useful. See you soon.